Well, I guess after the party yesterday, everybody has a little bit of a harder time getting up for the third day. So, but welcome to those who are here. Before we have our keynote this morning, our poster and demo chairs have a few announcements to make.
Hello, so we want to thank all of the poster and demo presenters. This year, the way we did our best poster and demo awards is that first we had a committee of jury members who judged the posters based on innovation, presentation, and potential impact. So thank you to our jury members for volunteering to do this. And the second round is now that we have a short list of posters and demos, the next step is for all of you to cast your votes for the ICCP Best Poster and Demo Awards. So here we have our short list of best posters. And you can find the demos and posters on this link here. You have until 11 a.m. to cast your vote, so please go ahead and vote.
And the link is also on the homepage as well, too.
Yeah, so the link is also on the homepage, in case you need it later. Okay, it looks like almost everyone has the link down. Still a few more people. So in addition to the voting for the Best Poster and Demo Awards, there is also the vote for the photography competition, which is also due at 11 a.m. And there's lots of amazing photos submitted, so please go ahead and cast your votes for that as well. Okay, I think everyone has the link down. So make sure to cast your vote for both these by 11 a.m.
Thank you, Kristina. So you should also receive an email with the two links, at least the ones who registered. Raphael will send you an email next few minutes, and we'll remind you again, during this morning, deadline is 11 a.m. So without further ado, it is absolutely my greatest pleasure to introduce to you our third keynote speaker, Sylvain Gigan. He obtained an engineering degree from École Polytechnique Palaiseau France in 2000. After a master's specialization in physics from the University Paris 11, Orsay, France, he obtained a PhD in physics 2004 from the University Pierre and Marie Curie in Paris, France, in quantum and nonlinear optics. From 2004 to 2007, he was a postdoctoral researcher in Vienna University, working on quantum optomechanics in the group of Markus Aspelmeier and Anton Seilinger. In 2007, he joined ESPCI Paris as associate professor and started working on optical imaging in complex media and wavefront shaping techniques at the Langevin Institute. Since 2014, he's full professor at Sorbonne Université and group leader in the Laboratoire Kastler-Brossel at École Normale Supérieure, ENS, in Paris. His research interests range from fundamental investigations of light propagation in complex media, biomedical imaging, sensing, signal processing, to quantum optics and quantum information in complex media. So this is the bio that Sylvain submitted. And of course, there's a huge number of awards and recognitions that he is too humble to put in his bio. But he said I shouldn't mention them, so I'll let you look that up on his webpage. So please welcome Sylvain.
Okay. Oops. Okay, so can you hear me well? Yes?
Is it on?
It should be on. It's good, I think. Okay, so thank you, Sabine, for the very kind words, and I'm really delighted to be here, and it's my first participation to ICCP, but I really enjoy the mix of topics and the very nice atmosphere. So thank you very much for the opportunity. And I will talk today about the work of my group about imaging with scattered light, and I will focus a little bit on fluorescence imaging for a reason that you will see that this is really where we have the most computational aspects. Okay, but first, before I start, let me acknowledge the group. This is the group as it is nowadays, with two permanent researchers, myself and Hilton Barbosa de Aguilar, who is a CNRS researcher, while I'm a professor at Sorbonne University. And a really nice group of people, PhD, postdoc, engineers that are really focused on this core goal that we have in the group, to a core mission to understand and exploit light propagation in complex media. And to start, I really want to start from the basics, which is this picture. There is a jet engine that is blowing some very hot air, and you take a photograph, so nice for ICCP, and you see that the photography is actually very blurred. And the reason it's blurred is because there is a jet engine that is blowing this hot air, and it's perturbating the wavefront. So you have a point source that should create a very nice plane wave, and this plane wave will be perturbated by the propagation, and it will give this blur, time-varying blur that perturbs the image. So the normal way to deal with that is called adaptive optics, and adaptive optics is about taking this aberrated wavefront, this perturbated wavefront, and measuring the wavefront in real time and correcting with an active element to cancel and flatten again such a wavefront. And when you do that, you can go back to a diffraction-limited image on your camera. So it's really a physical method to correct a priori the images. And just one example from astronomy, that on the left, this is what you do if you correct with adaptive optics the perturbation of the atmosphere from a ground-based telescope. And on the right is what you have if you don't. Okay? So this is nice, but you're trying to correct relatively weak aberration. And what I want to talk about today is about scattering, which is illustrated in this picture, where you have basically ballistic light, so unscattered light coming from the sun, very bright, very directive. This is what you shouldn't look at the sun. Then you have the blue color of the sky that is really single scattering, Rayleigh scattering, that's responsible for this blue color. And this is light from the sun scattered one time by some atoms of the atmosphere. And the multiple scattering process is, as I've learned from the group of Joachim Schechner, much more complicated than I thought, but it still can be understood as this multiple scattering process, that the light will enter the cloud and bounce for a very long time inside the cloud. So why is it interesting? It's interesting for many, many reasons, but what interests us mostly is we are opaque, we are multiply scattering, and this is a picture of the skin, and you can see that you can just see just the surface, or just a little bit underneath. And by a little bit, I mean it's defined physically by the so-called scattering mean free path, how long light can enter the medium before it gets deviated. This is about 50 to 100 micron in the visible and the infrared. And you have another quantity that is important for transport of light, which is the transport mean free path. How long does it take for light to be completely isotropically scattered? And that's typically a millimeter. Okay, so that gives you a range of idea of why it's complicated and how far you can go if you don't want to deal with multiple scattering. And this, there is a challenge in optical imaging that I think is well summarized in this graph, that you can use ballistic light. You can use ballistic light to, whatever. So you can use ballistic light to image with light. And on this graph, this is all the group of technique that you have on the bottom left corner. So you see resolution and depth. Depth is mean free path. So all these techniques over there, you don't need to care about the acronym if you don't know them, but these are microscopy techniques. They give you optical resolution using ballistic light, but they cannot go very deep. So they go a little bit beyond typically a mean free path, or a few mean free paths at best, because there is an exponential decay of ballistic light. And then you have a range of technique on the right, which are basically technique that allows you to go much, much deeper, but the resolution is much worse. So it's called diffuse imaging technique, which really are not really diffraction limited. and you typically would have a resolution that scales with depth, okay, of the order of depth, so a few millimeters at maybe a few centimeters deep. And the goal of the field of imaging would be to find a way to get images very deep using scattered light, but maintaining the resolution that optics should allow you to have in principle. So this is where we try to go. And it's an excessively difficult problem, so you have to go back to physics. And by going back to physics, I mean we need to simplify a lot. So really want to make the system as simple as possible in such a way that we can understand the basics and fix it. So this is kind of my visualization of our approach. And so the biological media for us would be something like white paint. And white paint is great. It's basically a collection of small particles. You can pack them together, and when it dries, it stays very, very static forever, or at least for a very long time for us in the lab. And with that, you can simulate and try to understand the basics of this kind of technique. Okay, and I want to illustrate with some simulation what happens when you have this multiple scattering medium. So you have like a ballistic pulse, and each scatterer here will emit a secondary wave. And you can see already this some kind of interference effect rising up and giving rise to these complex things. And you still have the ballistic light here. So this is actually a very weakly ballistic scattering system. So what's happened in practice is more something like that, where you have many, many scatterers. And in this case, you will see that the pulse will decay very quickly. So after about a third of the medium, you don't see it anymore. It's kind of gone. And now it's just multiple scattered light that will evolve in this medium and scatter for a very long time. So in this regime, which is this what we call this strong or deep multiple scattering regime, you have no more ballistic light. And light has been extremely strongly spatially, so in all directions, and also temporally stretched, perturbed by the scattering medium. And by perturbed, I mean much more than perturbed. But still, and this is the last point, it's a coherent and it's an elastic process. So in terms of waves and interference, it retained the ability to interfere perfectly. And everything you see here is a landmark of interference. And for those of you who are familiar with optics, this is what we call the speckle. So the speckle is really this multiple scattering interference result that mean that it's made of these grains. And each of these grains has the beauty is that it's diffraction limited. So this is just given by the angular range that can form this speckle at this particular position. So it has some kind of effective numerical aperture, effective size, and it's made of this slightly constructive grain and a lot of destructive interference. And also polarization will kind of mix it in a random way. It's also wavelength dependent. So because it's light stays for a long time inside, so it's very long path length. So if you change the wavelengths even by a small bit, the speckle can change completely. Okay, but still it's a complex distribution. So what I was showing you at the very beginning about using adaptive optics to correct for wavefront perturbation, the same concept should also apply in this extremely complex regime. So this is what we try to do. And to illustrate what we want to do, again, I'm illustrating again this different regime in this fog image. So you have some easy problem like ballistic imaging with this person in the foreground, so not a lot of scattering. Then you can see maybe this person in the background, which you can, in microscopy, you can use, for instance, optical coherence tomography, multiphoton imaging, light sheet microscopy, so anything that can select these few ballistic photons left and remove the rest, confocal microscopy. So then you can get some image a little bit deeper, but the problem normally arises when you really try to use only multiple scattered light. So what I will illustrate is that we want to do it at the same time with physics, and I will try to put, of course, we started to put more and more computational aspects and machine learning. So physics, first is we can really use the fact that it's a coherent process, and there was a lot of early work in the 90s in acoustics about doing what is called time reversal. So you use the reversibility of the wave equation. So if you have a point source that emits a small acoustic burst like this, the wave will propagate from this point source. And even if the medium is extremely complex, you can record on a lot of transducers some kind of long coda from this. And what you can do next is playback. And playing back, you need to play the end first because it's called time reversal. And the wave will be re-emitted and will refocus in space and time on your position. So this is really some early work of Matthias Fink, actually in France, in the Langevin Institute where I was. And we wanted to do this also with optics. And with optics, we don't have these beautiful transducers. We can't do time reversal, it's too fast. But we have spatial shaping tools with a lot of degrees of freedom, which you can see here, which are really this deformable mirror, liquid crystal spatial light modulators, and MEMS and DMD kind of modulators. So deformable mirror is really for adaptive optics. There's not enough degrees of freedom. But the last two is things that we can play with for manipulating the wavefront of light and playing similar tricks. And this, a very important experiment in the field was this 2007 paper with this date that I was mentioning before, from Velkop and Mosk, a group in the Netherlands, where they show that you can start from this plane wave giving you a speckle, and you can move to this second situation by putting a detector and optimizing the wavefront in such a way that you will try to maximize the intensity on this detector. And they found this extremely striking result that they can get one speckle grain extremely bright, okay? And the way it works is actually very simple, but first it's exactly like in adaptive optics, but it's in an extreme regime. So what they do is you play with the pixel of your SLM, and for each of these pixels, you keep the value when you vary it that maximize the intensity at your position of interest. And then you go to the next one and the next one and the next one. And what you do effectively is you start from this sum of contribution, which all have random phases, uniformly distributed phases, and pixel by pixel, you align them together. So you create this constructive interference, and when you do that, you will get this diffraction-limited spot, which is the 101 thing you need for imaging. Okay, so an experiment is actually very simple. This is our experiment in the lab from more than 10 years ago. You have a laser, you shine light on a wavefront modulator, then you go through your layer of white paint, and on the far side, you put some detector, for instance, a camera, typically. Okay, and what we introduced in the team back in 2010 was a kind of a generalization of this optimization method, which is you start from this SLM. This SLM is an array of input pixels, input modes, and then you have this linear system, and on the far side, you have a camera. And in between the pixel in and pixel out, you can define a linear mapping, so a matrix, that will describe the propagation of light through this medium. And what we designed was a method to measure this matrix. So what you do is you shine light on this SLM, and you send a series of patterns. So you send a basis of modes. In this case, it was so-called Hadamard basis, which was 0 and pi phase shifts. And for each of these modes, you want to measure the speckle on the far side. You need to do holography because you want to measure the field. It's linear on the fields. And when you measure this series of inputs, well, basically column by column, you are measuring your transmission matrix. So this was our initial method, but we kind of refined it after a while, and we actually could show, thanks to signal processing and a lot of help from colleagues, that even random or binary patterns also works. You don't need to send a basis. It's actually better to send more random patterns. And also you can deal just with intensity detection with proper phase retrieval algorithms. So with that, if you do this procedure well, after a few minutes in your lab, you will end up with a transmission matrix. And this transmission matrix will be, of course, totally deterministic as long as the medium doesn't change. It will have complex coefficient. And this looks like noise, but it's actually the realization of disorder that determine this transmission matrix. And this can be typically potentially of very large dimension. So it depends how many modes you want to send, but the medium itself can have a lot of modes, like millions in and out. Okay, and once you have this transmission matrix, what you can do is, for instance, focusing. So you can calculate what input pattern would give you a given output pattern. And what you need to do is phase conjugation. So you need to send at the input the transpose conjugate of your matrix, time the target that you want, and you can see that just as a time reversal operation. Time reversing the time is actually conjugating the phase. Okay, so this is the link with the previous time reversal experiment. And with that, you can do, for instance, you can calculate the pattern that would focus at one position, But then the advantage compared to optimization is you can just, you don't need to redo any measurements. You can just calculate another pattern to focus somewhere else, or to focus on multiple points, or to scan a point, or basically anything you want once you have this transmission matrix. And we also went the other way and try where the problem is now, okay, I'm giving you a speckle that I record through the medium. I know the transmission matrix. Can I determine what was behind? So we first did some, inverse problem, Tikhonov regularization to solve that, and this worked well. And we also did a lot of compressed sensing, so trying to use some sparsity priors to use the medium as some kind of random measurement machine where you can do this measurement efficiently. Okay, so that's it for that. But maybe just the take-home message is really that in optics, and in particular in photography, you try to get really good lens, right? You try to get the best lens that you can approximate as well as you can by a very simple transformation. For instance, in paraxial optics, you would describe a lens with a 2x2 matrix with just one parameter, that is the focal distance. And now what we're saying or claiming is that if you give me this piece of sugar, but I can measure its transmission matrix, which is of course many, many coefficients, I can turn it into a lens. And I love to use this slide in Switzerland because I can show that you can actually do much more than this, right? So you can actually make many, many functions, optical function. You can actually make it a very high numerical aperture lens. You can make it a polarizer. You can make it a spectral filter. You can make it a beam splitter cube. You can make it a circuit. You can make it many, many things. So we did many of those, or also other people in the field. But the take-home message is that you can now turn this piece of sugar or piece of white paint into any linear optical element or any combination of linear optical elements. So you can make a full setup if it's a linear setup with a special light modulator and this transmission matrix. Okay, and maybe that's, I only want to talk about imaging today, but in front of this crowd, I really want to say that we worked a lot on optical computing, and I have one slide to just give you an idea what we do. If you have this transmission matrix, it's like an input and output matrix multiplication. So you can understand it as a one-layer neural network where the weights are fixed, they are random and fixed, but it can be a very large dimension, typically million in and out, and you can go at kilohertz. So in terms of effective operation, it's actually a lot of operation that you can do at very low computational cost, and you have a nonlinearity for free at the end, which is this intensity detection. It's a modulus square, okay? And with that, we did quite a lot of work over the years. I just want to mention some of them, but really, if you're familiar with this concept, what we realize is this one-layer neural network, you can see it has a name in signal processing, which is random projection. So in a way, we have a random projection machine in hardware with which we can do some interesting signal processing. And it's never a standalone machine, but in combination with a lightweight linear regression or small neural network, it can be very useful. And we did for that image classification, things like reservoir computing and time series prediction, and with a modified version of that, which I cannot talk about today. We even went a bit further to do some feature detection, and it's a work of Faye Xia, who was talking yesterday in our group. Okay, but now back to imaging, okay? Back to imaging, I want to explain why it's interesting for imaging, and the key point is it's a lensless approach. So in a way, you may still have a lens, but the medium becomes a lens, and the resolution is given not by all the optical setup that you may have before your scattering medium, but it's given by the speckle size, which is given by the medium itself. So it can have, in particular, a relatively high numerical aperture, and the whole optical setup before become irrelevant in terms of optical imaging quality. The other ingredient that is important is the fact that in some cases you can actually move this focus around. And this is what we call a memory effect, which is not always there, but if your medium is thin or forward scattering, you have some memory that if you shift the incident angle, you can see that the pattern that you will generate can be also shifted, right? So in a little deterministic way, as you can see here. So that's valid for any wavefront. So if you send a plane wave, you will get a speckle. You can shift this speckle around. If you send a shaped wave and you have a focus, you can move this focus around. And it's particularly interesting for biomedical imaging. Okay, so the key point is I just told you until now how to go through something. So I'm able to put a detector on the far side, but that's not what you want to do typically in imaging. Normally, if you are not allowed to put anything inside, and you only have access to one side, okay? So the question how to use this wavefront shaping concept in order to focus deep inside the tissue non-invasively is not something I addressed yet, but this is something that has been really important for the community, and I can really mention this now almost 10 years old review, but it's still very much valid, about many different ways to go inside. And the first thing you have to do is you have to go fast. So tissue is not paint, it moves, it changes over time, so you need to do this modulation extremely fast, and you need to use efficient algorithms, but you also need to have a so-called guide star, by analogy with astronomy, where guide stars are used to measure the wavefront for the telescope, artificial or real guide star. So you need here to have a mechanism to monitor the intensity inside. And people have tried many, many things, like, for instance, nonlinear fluorescence, ultrasounds, photoacoustics. So many, many methods have been taken to do this. And I think one key message I want to give is that there is no silver bullet. So it's not like one is winning and it's clear that you have to use this one. So depending on what you want to do, how fast you can do things, what resolution you want, some of them might be better than others, but there's no clear winner at the moment. And what I want to cover in the second part of my talk is fluorescence. And fluorescence is particularly interesting in imaging because, linear fluorescence, because it gives a lot of light. You have, naturally some fluorescence expressed, so you can, inject some markers, but it's actually still one of the main tools used in biomedical imaging, but also in many imaging situations. So it's ubiquitous, but it's not a good guide star to date. So it's not in the list I was given before, where nonlinear fluorescence is there, but not linear fluorescence. But still, it's a very useful method. It provides a lot of light, which is good for if you want to go fast. So the group really tried for the last 7-8 years to find ways to use fluorescence to do wavefront shaping. And what I will try to show you is that you can still, even though fluorescence is an incoherent process, it's an incoherent light, you can still use the concept that I was describing before to do some imaging. You can shape and manipulate and exploit fluorescent light, and we can do some fluorescence imaging at depth and even some functional imaging that I will show at the end. But first, let me explain why it doesn't work normally to do fluorescence. And there was this first experiment in 2008, so right after this first paper, 2007, from the same group, where they said, okay, let's put one fluorescent bead inside a scattering medium. So I shine light and I see a little bit of fluorescence, but it's buried, so it's like a big halo. I don't see it very well, it's very wide. So I can optimize the wavefront, and then I get more intensity. So I know if I get more intensity, and I know that there is a single bead, that now I've concentrated my excitation on this bead. So it works well in this sense, and you've learned how to focus on a fluorescent object, but the problem is it fails as soon as you have multiple objects, because you will tend to distribute your light everywhere, but you will not have a guarantee that you will form a single focus. So on a single sub-diffraction limited object, you can do wavefront shaping. Beyond that is not possible with fluorescence. So what we try to exploit is the fact that even a fluorescent object can have some coherent properties. So in particular, you shine light through a scattering medium. Let's say you have one bead. This bead will emit some fluorescence that you can detect on a camera. And if this bead is small enough and relatively narrow bound, or the medium is not too dispersive, you can observe a speckle from this point source. So this fluorescent emitter can have it has some coherence that can show up in the speckle pattern of the camera. And the contrast can be very high, okay? Let's say now you add a second bead. The second bead will also be excited. It will also emit some light, but it will be incoherent with the first one. So what happens if you have incoherent imaging, you will add the intensity on the camera. So if you add two speckles in amplitude, the sum is still a fully coherent speckle, but if you add two speckles in intensity, you sum them, and then you get still a speckle, but the contrast has diminished a little bit. And you can continue, and you can see that the speckle will go down as you keep adding incoherent sources. Okay? There is actually a nice derivation from the early paper on speckle that the contrast scale with 1 over square root of the number of targets. And that's actually a very good number. It's actually a very slow decrease. So this is how you transition from a fully coherent to a fully incoherent object, but it's a slow decrease. So even if you have 100 or 1,000 beads, the contrast may still be measurable. A few percent is something you can measure on a camera. So this is why we'll try to exploit in the following, that even though a fluorescent object is incoherent, it can still have some speckle feature that you may be able to detect if it's not extremely large. Okay? So the first experiment is probably the farthest away from imaging, but it's still, we did some computational, it's actually something we did much more recently than all the others, so it's in reverse chronological order. But I want to show it because it's a nice computational problem. So what we tried to do was we tried to do some phase conjugation on the fluorescent sources. So normally what you do is you shine a laser beam, you would record a hologram on a sensor, and then you interfere with a plane wave to have an hologram, and then you can display this hologram back on the SLM, and you can re-emit this phase conjugate, and you can cancel the propagation. So this is digital optical phase conjugation, and it works because you have coherent light. Okay? So what people have done, and this was actually done in EPFL by Demetri Psaltis, is take a coherent object. So you take an object that can be coherently excited, and then you can, for instance, in this case, it was a second harmonic generation, which is a coherent process, and the light from this small object can be measured, and you can measure on the camera the hologram with a reference plane and send back the phase conjugate. So it works, but because you can have a reference. So the question is, what do you do if you cannot record a hologram? And this was solved by Yunse Beck, who is a postdoc in the group. And the solution he proposed, he implemented, was the following. So you have a set of point source. This point source will each have this independent speckle incoherent with each other. And now you put an SLM on the detection path. And you can take images, and you can display some pattern on the SLM. And for each of these patterns, you will modify all these wavefronts together, and you can record these intensity images on the camera. And he found this really nice reconstruction algorithm called mixed-state phase retrieval that was used in I think, X-ray diffraction tomography that allows you to basically solve this set of nonlinear equation for this multiple wavefront. And with this, you can basically retrieve from this set of images, you can retrieve the set of initial wavefront because you know this pattern. This is something deterministic. You know the SLM pattern, you know the output intensity, and you can find back the fields. Okay? And when you find back the fields, you can use this wavefront to refocus on each of those sources, which is what he showed in this picture. So you forget about the top, but on the left you see, for instance, 5 sources, and then on the lower part you can see that we can refocus on every of them. Okay? Okay, so that's if you have incoherent sources that are all emitting at the same time. But now what I want to show you is more some kind of active illumination scheme where you have some control over what you send, and you have now some sources that will fluctuate with respect to each other. And this is illustrated in this animation. So you have some sources. Each time a source emits light, you have a speckle on your camera, but then they kind of emit not always at the same time and not always all together. So what you will see, if you record a movie with a camera, you will see some kind of many time frames, which are basically all this speckle fluctuating in time. And the question we ask ourselves is, how do we go from this to retrieving the sources? Okay? And the solution is, again, algorithmic. We use non-negative matrix factorization because non-negative matrix factorization applies well here. We have positive sources, we have positive intensity speckle. So you can actually factor this complicated movie that you have here into a product of a low number of point source, each of them with a pattern and with some time evolution. So you can demix this, and you can estimate the number of sources from the data. It's actually very resilient to noise because of this non-negativity constraint, but you need the medium to be static. Okay, but if the medium is static, this works well. So now we applied it to various situations that I will show. For instance, we have this aspect, this canonical experiment where we shine a pattern and we have a medium that is, we consider it as a black box, which is some scattering medium and some fluorescent object on the back. Okay, and we have some input and we have some outputs. Input patterns, output intensity images. So the question we ask ourselves is, we can describe the propagation as a forward transmission matrix to excite the object, and then as an outgoing transmission matrix, which is actually 4 incoherent lights. It's some kind of slightly different from the transmission matrix. It's like some kind of positive matrix that describes the light from the object to your camera. And what we wanted to do is, you can write an image formation model like that, and we wanted to determine this forward and backward transmission matrix, and be able to focus on the target or reconstruct the object. Okay, so that's the setup. We shine many patterns, random pattern. We record many intensity images. And the first step we do is this non-negative matrix factorization. So from this set of output measurements, we can retrieve the speckle pattern from each of these point sources and the temporal activity of each of these point sources, okay, how they were excited. So now it's like we had a detector inside, because we know the intensity on each bead as a function of time, and we can run phase retrieval in order to retrieve the forward transmission matrix, okay? So the first step gives us W, the second step gives us T, and if we have now T and W, we are in business and we can do some imaging. And for instance, we could show that we could focus on the different targets, but I mean, focusing is just a proxy for imaging, so I want to show you imaging. So imaging, now we want to use this correlation. So we want to exploit the fact that we have this memory effect that kind of tell you a little bit more about the position, the relative position of these different sources. So if you take two sources and two patterns from two sources, so you don't know where they are with respect to each other, but actually if you cross-correlate these two speckles together, you will see a shifted peak that will tell you that these speckles are, of course, they are different, but they are also, they have some correlation that depend on the relative position between those two sources. So I'm able to tell from these two patterns the relative position between source 1 and 2 that created them. And if I do that for every pair I have, I can actually reconstruct the position of my sources by near neighbor. And the good point is it also works even beyond the memory effect, that is this circle here. So I can do some decent reconstruction. Okay, so we are physicists in Central. We always want to simplify as much as we can. And we say, okay, let's try to throw away the most expensive piece of the equipment in the setup, that is the SLM. So can we, at the end, what we need is we don't need to know exactly for this particular experiment what we send. We just want a fluctuating illumination. So let's throw away our 25K SLM and let's replace it by a $5 rotating diffuser and a motor. Okay, so we now have a rotating diffuser to basically generate some fluctuating illumination. And this fluctuating illumination will do exactly the same. They will excite this object dynamically and with a spatially variant illumination. And on the camera, we will record this set of patterns. Okay. So then we could do exactly the same, but also faster and cheaper. We start again with this intensity pattern. We deduce the fingerprint from each target, and then the cross correlation will give us the relative position between this target. And this time we can go. Actually, this is quite fast. We are not limited by the speed of the SLM, and we could reconstruct relatively complex objects, even continuous objects can be reconstructed this way. So you have the ground truth above. It was just pollen seed and some cellulose fiber that we stain with a Stabilobos. So it's a very, very simple experiment, and we could reconstruct them. Also, you don't need that many patterns in principle. So of course, the more pattern, the better. But here you can see for this object that is this pollen seed, just the number of patterns, even with just a few hundred. So this can take maybe a second if you have a fast camera. You can reconstruct something. Of course, the more pattern you take, the better the image is. But you can still get some decent reconstruction in a fraction of a second in principle. Okay, so the take-home message is, with this rotating diffuser, I cannot focus anymore because I don't have access to the forward transmission matrix, just the backward transmission matrix. But I can reconstruct, and we did reconstruct up to about 100 sources, more or less. So that's the rank of the non-negative matrix factorization. Beyond that, it starts to be a bit dodgy, but it doesn't mean that it cannot work with more effort. But that gives you some kind of rough order of the complexity of the object you can reconstruct. It's actually quite fast and flexible. Okay, so what we try to do next is actually to go a little bit beyond that. And of course, everybody is doing a neural network. So we said, okay, why not us? And actually, there was some prior work already, right? So people have tried to use a neural network like this, a ConvNet, in order to, mimic these input-output pairs through a scattering medium. And they could show in this paper that, you can learn and how to focus through this medium, okay? This is nice, but it's actually not physical, right? So ConvNet is actually not describing well what happens through this medium. So this paper, for instance, was a nice improvement over that, because in this way, they were trying to mimic this input transmission through the medium by taking a one-layer neural network with complex coefficient. That's good, because now this is more physical, because the system is a one-layer complex transmission matrix. So this was, for me, a nice step forward. You have now some physical realism, and with a much, much simpler network, you can get something similar to that, and you can generalize to unseen type of images, et cetera, et cetera. So it's much nicer. And we got inspiration of that, and we tried to apply to our problem of seeing inside. And this is a work that was done by Alexandra Darko, and Feisha was also involved, where now you take this system, and you have to think of it as you have to unfold it. Okay, so you have to think of it as I'm sending some pattern through my medium on my target. So I have one transmission matrix here, one nonlinear target here, intensity, and then another layer to go back to my camera. So if I want to explain it in terms of neural network, I need a two-layer neural network where this is my input layer, my object is my hidden layer, and my camera is my output layer. Okay? So now what you can do is you can interrogate your medium, so you can send input-output pairs, and you can train this two-layer neural network in such a way that you can map these input-output pairs correctly. And if you do that, you're basically learning the transmission matrices. Okay? So that's, the idea was enticing, and it works. It's not great, but I will show you some very simple results. It doesn't work on very complex objects yet, although we're still working on it. But here we had this object with a few beads with white light, and we could show, once we learn the matrix, we can then, check that the way to check that we have learned the system is to be able to focus on these beads, and we can show that we can focus on these beads reasonably well, and this is something that we want to push forward. One nice advantage of that method is that it's not limited to fluorescence. Okay, so fluorescence, you have this beautiful non-negative matrix factorization algorithm that does all the job of eliminating noise for you. But it works because fluorescence is positive. But if you have a coherent process, it's not working because you have negative values too, right? So what you can do is you can actually apply this two-layer neural network to different contrast mechanism, and you can change the type of nonlinearity that you have there, and you can change whether you sum in intensity and phase, and whether this is a kind of positive or complex values, depending on the modality of imaging that you're doing. And we could show that, coherent or incoherent for different higher order of nonlinearity, like linear fluorescence, 2-photon fluorescence, 3-photon fluorescence, Raman, second harmonic generation, third harmonic generation, all of this can be mapped into this. So we have only simulation, but at least in simulation it works very well. So what we like here is really that we can generalize beyond this fluorescence imaging that we demonstrated experimentally. Okay, and for the last result I want to show is I want to move to fluorescence imaging, but I want to move to a situation where I'm not using active illumination, but I have a system that naturally has some fluctuating fluorescence. And this is the case in neuroscience. So in neuroscience, you genetically modify animals in such a way that whenever the neurons fire action potential and talk to each other, they will become fluorescent. So this is a video of zebrafish that you image, and you see all these neurons lighting up and talking to each other, which is fascinating. And this way you can unravel of course, the behavior of the brain, and play some tricks of showing object to the animals and looking how it responds, etc., some stimuli. But it works because the zebrafish is transparent. Okay, so zebrafish is small, it's transparent, so you can look at all the neurons at the same time. But it doesn't work in a more complex animal. So then you have to do some tricks. You have to do 2-photon imaging, etc. But you're still limited to upper layers. So what we try to study is, can we apply this technique that we have to, in principle, be able to decode some neuronal activity deep inside the tissue, for instance, a millimeter under the tissue. In this case, our hope was that you would still see a little bit of speckle, and you could use this non-negative matrix factorization. So even though the sources are not even diffraction limited now, so neurons are 10 micron in size, so they're actually much bigger, but still we were hoping that we would get a little bit of contrast. Okay, so this is the synthetic proof of concept experiment we performed. So the setup is really beads, so 10 micron beads. So we took beads that were much bigger than before. They give more signal, but of course the contrast is lower, and the light goes through the skull. So we were given some skull from animals, from mouse, from our neighbors' collaborators, and this is really opaque. So it's a little bit like a layer of white paint, but through it you will see the speckle, and you can record these patterns. And then what we do is we use a DMD as a way to excite these few neurons with some codes in time that we took from database of recordings. Okay, so it's really biological, meaningful excitation signal. Okay, and what we record on the camera is exactly this. And as you can imagine, non-negative matrix factorization allows to retrieve the speckle pattern from each of these, and as you will see, the temporal activity. The key point here is there's no shaping, there's no SLM, there's no rotating diffuser, and you don't need to know the transmission matrix. You just excite with continuous light, and you wait for the fluorescence to happen. And this is the result we had. So you can see some temporal activity. This is the ground truth, and we can retrieve, with this non-negative matrix factorization, we can retrieve quantitatively well the time trace. And we could also verify, because we know the ground truth in this case, it's a completely synthetic experiment, that we can retrieve not just the time trace, but also the speckle pattern from each source with a decent accuracy. So that was 2020, and we did some work in the meantime. In particular, we could show that using this footprint, we can actually also localize the relative position of each neuron. Of course, not very precisely, but we have a little bit of localization ability. And we had a very nice collaboration with a team of neurobiologists in Rockefeller in New York, to show that at least in some very, very simple case, like a couple of neurons, and it could be done in vivo. Okay, so that's just a very recent result that they publish. Okay, and the last thing I want to show is that we try to push this idea to endoscopy. So endoscopy is you stick a multimode fiber inside an object to measure something. So the multimode fiber will be a very small footprint endoscope. And what we try to show is through this miniature endoscope, you can still do the same trick of recording some different fingerprint from different neurons. So of course, the multimode fiber is not very long, so it's not speckled yet, but it still allows you to demix them, and we could retrieve some activities of about 10, 20 sources below this endoscope. And the hope, this is what we do now with our biological collaborators, is to be able to make a small miniature head-mounted system that we could record some very deep activity with that. So this is the miniscope. It's a commercial fluorescence microscope that we adapted to put a very thin piece of multimode fiber to it. Okay, so I'm at the end of my talk. I try to convince you that biological tissues are complex, but this complexity can be exploited because we understand the physics of this multiple scattering process. Shaping can be used to undo or cancel this scattering, and I was showing you optimization, phase conjugation, transmission matrix approaches. All of them have their pros and cons. So transmission matrix is the slowest, but give you the most information. Phase conjugation can be slow, can be very fast, but you need a source. So they all have their pros and cons. It's not always needed. So I was showing you some cases where even without wavefront shaping, you can still do some imaging and demixing. And this understanding of the scattering can help a lot. That's a big lesson. So I think it's still something where physics is very helpful. And this last part I was trying to convey was that incoherent light is still possible. Fluorescent light is still possible. And this computational tool that are available, like machine learning, non-negative matrix factorization, phase retrieval, matrix completion, we used a lot of other things that I couldn't show today, are very helpful for imaging. And of course, there is many challenges left in order to get images comparable to what people do in microscopy. We are very far. There are many problems of speed. So engineering problem, computational problem, physical problem to overcome. So it's still not yet in every microscopy lab. It's still some physicist baby step, as I try to call them. But it's a very exciting field, and I think it's a very nice blend of physics and computation that we like to play with. So with that, I want to thank again all my team and collaborators, which were really instrumental in all the work that I was showing today, and you for your attention. Thank you very much.
In a number of the figures, you illustrate the fluorescent targets as being on an isodepth plane. To what extent is that necessary?
You mean a single depth?
Yeah.
Yeah. So indeed, yeah. So the memory effects tell you that two sources shifted relatively to each other will be, just shifted speckles, so you can do cross correlation very easily. So it doesn't stop there. So the memory effect also extends in Z. So if you have a source that is moving up and down, it would also shift the speckle, but in a more complex way. So it would be some kind of, magnification, demagnification. So it would be like applying some kind of phase ramp, spherical phase ramp on the speckle. So you cannot. It's more complicated than doing just some, cross correlation between multiple images. But in principle, you can do some 3D reconstruction if you want.
Thanks.
It's just more complicated.
Hi, Sylvain. Thank you. Do you ever run out of pixels? Can you talk about the challenges of imaging the speckle? Because we can see the speckle in many different planes,
Yeah.
and it's constantly evolving. And then I assume that if you have an n-by-n transmission matrix, you can only capture like n
Sorry,
scatters.
I missed the beginning of your question. So what did you say about the speckle?
Challenges with imaging and characterizing the 3D speckle.
Yeah. So in our case, we are only interested in the speckle in a given plane, which is the CCD plane. That's what we record, right? And you mean about inside the object? Or
Do you run out of pixels, like aliasing, for example?
do we run out of pixels? No, we don't run out of pixels. So typically the pixels are, we have millions of them, right? What we want is we want to resolve the speckle grains. So typically, we don't want the speckle grain to be smaller than the pixel. But typically 2 pixels per speckle grain is enough. And at least for everything we do, we are not limited by the pixel counts. So I'm not sure if this answers your question. Feel free to elaborate if I didn't really answer.
I'll ask you later. Thank you.
Yeah.
Other questions? There's one back and then one back there.
So in the you resolved the neuron signals over time, and then you said you had an optics express or something where you did a little bit of localization. I guess what was the gist of that paper? I guess how was localization done with?
So what we do is, so this I can explain. So what we did in this first paper, we were just interested in recording the time trace, right? So we just verified that the speckle pattern that we had was corresponding to the ground truth. But just like in the spirit of all the other work where we could really cross-correlate this fingerprint and retrieve the relative position, we could show that we could also do the same here. We went we simplify the system even more by taking a thin scatterer instead of the skull. I mean, the skull doesn't have too much memory effects, so it would be maybe difficult to find the relative position between two neurons that are too far apart. So with a thin scatterer, a surface scatterer, we could do it very cleanly. But the idea is you don't find the absolute position of a neuron, you find the relative position between neighboring neurons. Is that your question? Okay.
Okay, so thank you for the great talk. So I'm interested in simulation of lots of physical phenomena used in imaging systems. So, for example, like standard imaging, there is a great tools using Monte Carlo simulation, such as path tracing to reproduce the realistic images. And I wonder if there is also kind of Monte Carlo simulation to reproduce the speckle patterns.
Okay, so I mean, okay, I'm not sure I fully got your question, but if I understood well, you ask about trying to use some simulation to kind of predict, for instance, the transmission matrix or something like that?
And so reproduce the speckle pattern.
Yeah, so for me,
Yeah.
reproducing the speckle pattern is kind of predicting the transmission matrix from simulation. So I can answer that. So the general idea is you can always do some Monte Carlo simulation that will produce some beautiful speckle. You can even simulate in silico some transmission matrix of a very large system. That works perfectly, that's no problem. The problem is really to be able to do to find the specific transmission matrix of a system you have in the lab, right? So for this, you would need to, in principle, know the exact refractive index distribution, and from that, to compute for this particular medium what is its transmission matrix. And that's extremely challenging, both physically and computationally speaking. So in a way, by measuring the transmission matrix, by sending these input-output pairs and deducing the transmission matrix, you really measure the transmission matrix of a system in the lab that you have and that you can play with, right? So what you say is fully correct. You can do it, but it will not help you to image in the lab a particular sample. Does that answer your question?
Yeah, okay. And also I have another question. So today you showed several...
Okay, yeah, happy to continue afterwards. Yeah.
Okay.
Yeah.
Another question? Yes.
Just a quick question. Are you, with the spatial light modulator, are you able to control the phase of the light, or is it just amplitude modulation?
So yeah, so we can do both. So with a phase modulator, like a special light liquid crystal modulators, you typically control the phase. With a DMD MEMS modulator, you typically control the amplitude. So you just have 0 or 1 amplitude modulation. But whatever the tool you use, you can always use off-axis hologram generation in such a way that with proper filtering, you can in general generate any pattern. Okay. The problem would be efficiency. So, but in most of the things I was showing today, it was phase modulation.
Very nice talk, very interesting. If we want to go from imaging individual sources with fluorescence, let's say under the scattering medium, to a more general type of imaging problem where I want to image a slice. One issue with the transmission matrix and all these matrix-based approaches is that it's basically a mapping from 2D to 2D. So how do you even choose the plane to image?
Yeah, so that's a very good point. So it's a 2D to 2D, of course, modulation in, modulation out. The medium is 3D itself. So what people have been doing is methods to measure some kind of time-resolved reflection matrix. So people can do, like in OCT, you can do some kind of gate in time, and you can measure the arrival time of photons as a function of time. There is a beautiful set of work there's some in Paris, there's some in Korea, for instance, where they use this reflection matrix, time-gated reflection matrix. And then, of course, it's a much bigger information because it's input, output, and time. What we did in our case was input, output, and wavelengths. So that's something we did in the group. But this time information is also very interesting. And then they kind of get some kind of depth resolution. And they have also some method to separate multiple scattering from single scattering in a very efficient way. So with this kind of technique, they can get some pretty nice 2D images, but that's still in a regime where they manage to extract single scattering component very, very weak, like 10 to the minus 10 ballistic components. So what I'm describing here is technique that could in principle go when you have no ballistic light at all. So, but what you say is it can be done. Yeah.
Thank you very much. Very nice as usual. I have a question regarding the sugar cube. You mentioned that can be any kind of circuit, optical circuit for computation. How do you envision modeling, more than modeling, programming that potential? I mean, I assume that you have in mind different types of configurations, and how do you see that the programming happening?
Well, yeah. So
or you see that kind of a different sequence, and then you just pick and you adapt to what it is that you want to do.
Yeah, so the general idea would be that if you know the transmission matrix between your SLM and your pixel, you have millions of mods in, millions of mods out, and from this knowledge, you can basically define a set of input modes, define a set of output modes, and kind of find the wavefront that will reproduce between this set of input and output a given linear transformation, smaller dimension. Like maybe you have a 10 by 10, for instance, something relatively simple, or few tens typically is something we can do. It will always be a very lossy operation. So that's one point that you trade. So you always, even for these focusing experiments, the energy in the focus is actually very low. So the SNR can be huge. If you measure on many pixels, you can get an SNR of 10,000 to 1 to the background. But if you have 10,000 in the focus, but you have a million speckle grain 10,000 times lower, that's still 1% of the energy, right? So you can do this kind of mapping, and I think it's not an easy computational problem to calculate what wavefront you have to display to get a specific linear operator, but you can do it. A big drawback is efficiency, energy efficiency. I'm not sure if it answers your question.
You just have one configuration. So what God gives you, it's what you use. It's not that you can model.
Yeah, well, I can program it on the fly, right? So I can have a set of let's say I have a set of single mode fibers that arrive on one end and set of detector on the same, and in the middle I have an SLM and a scattering medium. I can absolutely program my SLM in one shot to get a specific linear operation between these modes, and I can recalculate and change it on the fly if I want.
Any more questions? Otherwise, let's thank our speaker again. Thank you so much.
Thank you.
Okay, we'll have a coffee break till 10:30. Do not forget to vote for best paper demo and photographic competition. It's open till 11. And for those of you who've left the poster yesterday and would like to recuperate it, please do that during this coffee break. So we'll be assuming that after this coffee break, everything that's still hanging there can be recycled.